I'm just giving a brief something knowledge sharing on VLSI topics. Okay.
Okay.
Yeah. Can you did you remember Moore law?
A little bit, not that much.
Okay. So Moore is who is Moore means Moore is a founder of Intel company. Okay, he is the co-founder of Intel company. He introduced the integrated circuits. Okay, present we are using the integrated circuits, right? Integrated circuit is nothing but the transistors. Number of transistors are integrated in a single chip. Okay, based on the small scale, medium scale, large scale, like that we are getting advanced chips. Okay, so what Moore has predicted means in 1965 he predicted that the number of transistors and integrated circuit will double for every 2 years. Okay, and the size of the transistor will be reduced for every 2 years. Every 2 years means approximately it is 18 months. Okay, suppose if I show what Moore exactly means. Suppose see when we are in 1900, at time of 1900. Okay, in the year 1900, suppose we have used the transistor with 10 transistors in a chip like this, 10 number of transistors, and in 1920s we have used like 100 number of transistors like this. 100 number of transistors means, suppose here the size if you take it is in some micrometer. Okay, then it reduced to 100 micrometers to 50 micrometers, suppose in this case. And then 1940s, suppose if we use 1 lakh number of transistors. 1 lakh number of transistors means what is the size? Maybe it is in 1 micrometer if you take. Okay, 100 micrometers to 50 micrometer it reduced, 50 micrometer to 1 micrometer it has reduced. Okay, then in 1960, in 1960, suppose a 10 lakh or 100 lakh number of transistors we are integrating in a chip. In the size, maybe you can consider 100 nanometer size. Okay, in 1980, suppose we are using, in 1980, suppose we are using 10 lakh or 1 crore. Okay, 1 crore means maybe the size is like 80 nanometer if you consider. Okay, in 2000, we are using like a 10 crores or million number of transistors. In that case, the size of the transistor may be 50 nanometer. Okay, now 2020. In 2020, what is the size of the transistor we are using? Can you guess?
I think 25 nanometer.
25 nanometer? No. It is just I took no, approximately, not fixed
Yeah.
values. Okay, in 2020 or now in 22, we are using a 5 nanometer technology in present AMD processors. Okay, whatever we are working on the present processor, we are using 5 nanometer transistor. Okay, did you see?
Okay.
This is nothing but a Moore law. What he predicted means exactly that is correct. Okay, for every 2 years the number of transistors increasing, doubles. Size of the transistor half. Okay, what is the advantage in that case means, if number of transistors increase means what happen? Number of switching transitions will be more. Number of switching transition more means speed is increasing. Okay, speed is increasing and area is also reducing. Size of the transistor is half. That means area automatically reducing, right? So that is nothing but Moore law. Okay, area, speed and power reduction. Power automatically we will reduce by using there are a lot of power technique mechanisms out there internally. We will use the power technique mechanisms and we will use power reduce techniques. Okay, this is a Moore law. Okay, present we are using 5 nanometer technology, right? What is mean by 5 nanometer? First of all, what is mean
It's
by
nothing
5
but the
nanometer?
size.
The size of the transistor. What is mean by
Transistor,
size of
yes.
the transistor? How can we tell the size of the transistor? Suppose,
Um,
can you tell me which transistor we are using? Don't feel bored. These are just the
I don't
basic
know. I'm not
topics.
feeling bored. Yeah. uh,
Some people what
uh,
they think means we are coming design verification. Why you are telling all these things? They will
I
think.
know.
Yeah, just for
Yeah.
VLSI things. Yeah.
Yeah. Like actually, uh, I forgot those all the
Okay.
like yeah.
So tell me just what transistors you know.
FET transistors, MOSFETs.
MOSFETs.
Yeah.
MOSFETs, a
Yeah.
CMOSFET. Okay.
CMOSFETs. Yeah.
Okay. Suppose if we take the CMOSFET, if for CMOSFET there will be source, there will be drain, and
Drain
this
and
is the gate. Okay,
gate.
right?
Yeah.
And this is some bulk and all. We have the terminals here. So here, what is the size of the transistor? How can we calculate? How can we tell?
It's I think it's a time taking from source to drain or source to gate,
Okay,
something like that.
source to
Yeah.
drain. Not time taken. Suppose here the electrons move always from source to drain. Okay, this
Drain.
is
Yeah.
nothing but the channel width. This
Yes.
is the width of the channel. That width of the channel is nothing but the size of the transistor. Right.
Okay.
Suppose
Yeah.
we are using 5 nanometer. Suppose if we tell this is a 100 nanometer transistor and 50 nanometer means size will be very less. 5 nanometer present we are using. That means very, very minimum size between a source and the drain. Right. This is 5 nanometer. Suppose if transistor goes to 1 nanometer, what happens? Very thin. If
Yeah.
transistor goes to 1 nanometer, what happens?
Maybe I think it might like the speed might increase.
The speed might increase. Okay. Will it work as a switching operation? Transistor is nothing but here we are performing the switching operation off and
Yeah.
on. Based on we are doing all such things. Will it work? Switching operation, will it work here in 1 nanometer?
I think no, maybe
Why no?
like they might get into single. Uh,
See, in that case, what happened means because here there is very thin layer in nanometer, very thin layer between source and the drain. Maybe it will get short circuited with each other. If it short circuited, total chip will be collapsed, right? And
yes.
power current leakage will be more. Current leakage in the sense the current will leak more. Okay, so in 1 nanometer we won't use the transistor. Okay, so beyond 1 nanometer, what is the technology we can come? Transistor dead means VLSA will be dead.
Yeah. Yeah.
Then what is the
Um,
alternate technology?
I don't know.
Okay, alternate technology is nothing but before that we'll tell discuss. You understood Moorla, right? How the
Yes.
transistors are integrating everything, right?
Yeah. Yeah.
So this is a CMOS transistor. Okay, present we are using not CMOS. CMOS is up to 22 nanometer. After CMOS, we came to FinFET transistor. FinFET is also up to 10 nanometer only. I told now 5 nanometers, right? 5 nanometers means we are using like GAFET, okay, MACFET. There are different types of FETs are there internally. Okay, they won't release all those names and all. So we are using those type of FET. Okay, what is the difference between CMOS and FinFET means nothing difference is there. Like CMOS, we will connect this source and drain all in a planar model like this horizontally. When it is in horizontally, when it reaches to 25 nanometer, that is a very minimum distance between a source and the drain. Okay, so the leakage current will be increase. The short circuit effects will become. Okay, leakage current will be more. So that's why we are just using the FinFET. Okay, from this CMOS we are just changing the directions of the source and the drain. We are using the FinFET, which the source and the drain are connected in horizontally in this manner. We can avoid some current leakage and some short circuit effects we can avoid. Okay, up to 10 nanometers. Then up to there is a graphite like a gate all around, all there. Okay, if you are interested, you can go to all those concepts you can get. Okay, so I told that what happens if it reduces to 1 nanometer, right? 1 nanometer means it will get short circuited, we cannot use the transistor. Okay, so in that case we are moving to the quantum technology. This quantum technology is not there now, it will come in next 20 to 15 years. It is under project only. Okay, so quantum technology means here we don't use any physical transistors and all. Okay, in transistor there will be electrons, right? Whenever the
Yes.
electrons are moving, okay, based on the electrons movement, maybe you know the spinning concept. Electron has the spin property. Okay, spin property means what? Like spin property is nothing but when suppose when we toss a coin, it may reflect to head or it may get to tail. Okay, like that
Yes, like
electron
probability.
also, yeah, like electron also had a spin property. Okay, based on the spin property, if electron like head, if it is a up spin means based on the magnetic field we will put some artificial magnetic field around that. Okay, based on the artificial magnetic field, based on the spin, we will store the data. We are going to store bits 0 or 1 in the electron. Okay, spin up means it is a 1 bit, spin down means it is a 0 bit. Sometimes not up and down, that means not a head or not a tail. Sometimes it will rotate in middle, like it stand. Okay, in that case spin up and down. Okay, like this, spin up and down. Here also we will give the artificial magnetic field and we will store 2 bits at a time. That is a main advantage of quantum technology. Okay, there are so many topics in quantum technology. You need to learn, you need, if you want to go through that, you need to go spin spin property, entanglement is there. Internally there are so many subtopics. I'm just giving the uh, brief things. Okay, what is the technology and all. Okay, so here we can store based on the electrons, based on the spin property. Okay, if you see here, we are storing 0 bit, we are storing 1 bit, and the spin up down means 1 0. That means at a time we are storing 3 types. Okay, so that is a main advantage of quantum technology. Okay, the speed of quantum technology is 40 million times than normal technology. You know, normal computer, that is a very much a speed. Okay, and can you tell me what is the disadvantage in this case if we store the data in electrons?
I think we might lose the data.
It might lose data in what conditions?
Uh, no idea. And no guess.
Okay,
Like
see, you're telling that electron always it will be rotate. Okay, when
yes.
always it rotate means we are storing the data. That means we need to keep the electron constant. Okay, if we want to keep
Mhm.
electron like a constant, we need the temperature. Whenever the temperature increases, automatically the electron won't be constant, right? So we need to check the temperature here. Mainly we need to keep a very low temperature, like a minus 0 degree centigrade. Okay, very coolest place. That's why quantum technology is somewhat difficult for normal usage. Okay, these computers maybe we will use only in labs. Okay, that mean for weather reporting or for like for certain conditions, like for weather reporting or in doctor hospitals. Okay, some monitoring, all these things we will use quantum technology, but not normally. Okay, because
Okay.
we cannot handle that, and it will do very high speed, which are used for uh, those applications only, not for normal usage. Okay, that is what the quantum technology. There is so much information we cannot discuss in this session. Also, if you want, I can tell again about the quantum technology, what and all. So that is the upcoming technology after transistors. Okay, Got clarity? Any doubts?
For the clarity.
Okay. And next VLSI design flow. Okay, you already know, I think so. You already know what VLSI design flow happens. Okay. As you told that there is a design idea. Yes, we will take one design idea. Suppose some processor, suppose we are using some processor in AMD, like granite rich processor previously. We will take all the considerations, all features will be taken, like power, not only power, area, speed, there are internally so many features will be there. We will take all the features into consideration, and we will check what are the updates we can give, what are we can remove. Okay, all these things we'll check, and we'll come to one design flow. After taking one design flow, we will draw the architecture. Some micro architecture will be drawn. Okay, suppose I am taking for a risk processor. Suppose for risk processor, this is the architecture. Okay, there is a fetch logic, program counter block, and there is a register block, control unit, ALU, store logic block, data memory. This is some micro architecture. If you take SOC, it will be big one. Okay, so many things will be included in a SOC. So we'll get one architecture. Okay, after getting the architecture, what happens means, the behavioral description. Okay, if you take a SOC, there are so many sub modules will be there. Each team will be assigned one module. Okay, based on that, the design engineers will design each module. After designing each module, they will connect all the modules at a time, and they will check the design is working correctly or not. Okay, after the once the design engineers the design completed, they will send to the verification engineers. Okay, the verification engineers write the very code, like if you see, there are IPs, there are SOCs, subsystems are there. They will write UVM SV code for verification. They will do the verification and all, they will check. In verification also, we'll have so many things. Okay, like validation. If you know validation, after verification we'll do the validation. Okay, pre-silicon validation, post silicon validation will be there. After verification, it is just verification means what, just checking the functionality, checking, writing the test cases, and just checking the functionality. Okay, whether the output is working correctly or not, output is getting correctly or not. That is verification engineer. Internal verification engineer also, there is a DFT team, design for testability. There is a DFD team, design for debug. Okay, DFT is a testing which is done in a pre-silicon. Okay, pre-silicon means what, before doing the manufacturing. Okay, before doing all like tape out things, before doing the silicon fabrication, everything, we'll do the pre-silicon testing. That is nothing but DFT. Coming to the DFT, after doing the silicon tape out everything, internal, why we are going to DFT means, suppose in modern complexity is increasing more. Okay, pre-silicon verification is no more, that is not sufficient step to capture all the design bugs. Okay, bugs are escaping. If we can tell, bugs are escaping. Okay, so it is not sufficient. That's why we can catch the bugs in post silicon. Post silicon validation has a mandatory verification nowadays. In present SOC, it is a mandatory. So once the tape out done, we'll get a silicon validation. It is a like extra piece of hardware we are putting. Okay, by putting extra piece of hardware inserting into the SOC, we will do the silicon bug in post silicon. Okay, why it is mainly means, it will help the providing visibility of internal silicon things, if there are any bugs internal, after designing. Okay, so that is a validation, DFD validation. Okay, but all these things, like we need not to learn before. Once we will enter as a design verification engineer only to the company. If you want to enter into any company, we'll enter as a design verification. In that, they will assign all these blocks, how DFT, DFX, there are so many things out there. Okay, that is a verification, pre-silicon validation and post-silicon validation. And then After all these things, after all this testing done, then we'll do the actual manufacturing process. There they will do tape out, physical design, fabrication, they will check like routing and placement, all these things happen. Okay, did you understood? All these things will happen before only. In post